Hello, today we're going to talk a little bit more about probability, and in particular we're going to talk about a different type um, of experiment that's a little bit more numerical in nature, and it allows us to do something extra with our probability. So when we talk about a random variable, it is a probability experiment whose outcomes are basically numerical. So for that reason, we get this distribution. Distribution is just a table that describes the probabilities of the different outcomes. And the rules for a probability distribution is that the outcomes are numerical. And typically what we do is we denote them as the probability of capital X. Capital X is the random variable itself. You can kind of think about that as like in some sense telling us what outcome it is when we set x equal to a lowercase x. So the outcomes are denoted with these lowercase x's, and they're numerical, and when we want to talk about the probability, we set kind of the capital X equal to the small x. All the probabilities have to be between 0 and 1. That's just like any probability experiment. And the way we can write that is that if I talk about each individual probability, I set it between 0 and 1. And if I add up all the probabilities, I'm supposed to get 1. All right, so that's what a probability distribution is supposed to look like. So let's take a look at an actual distribution. So here is a probability distribution. I'm calling it for bonus points. And what we're seeing here is that we've got these different values. So up in the top row, we have the values 10, -5, 15, -25, 5, and 0. In the bottom, we have these probabilities, and each probability is 1 out of 6. So what I need for my probability distribution to work is that, first of all, each probability, so if I look at each of the individual probabilities, each of these individual probabilities need to be between 0 and 1. So 1/6 is between 0 and 1, 1/6 is between 0 and 1, and so on and so forth. The second thing is that if I take them all and I add them up, if I add up all the probabilities, I've got 6 of them, and they're all 1 out of 6. So I get 6 out of 6, which is equal to 1. And so that's also true. So for a probability distribution, every probability has to be between 0 and 1. And when I add them all up, I have to get 1 or 100%. So this is a random variable because the outcomes are numerical. So notice that we have numerical outcomes, 10, -5, so on and so forth. And I get a probability distribution because it follows all the rules. So the reason I'm calling this the distribution for bonus points is because what I want you to do is to imagine that this is the way that I assign some extra credit on the upcoming exam. So how would I do that? Well, how would I conduct an experiment that has this distribution? These all have a probability of 1 out of 6, so maybe I attach each of these outcomes to the rolling of a die. So this 10 would be if I roll a 1, -5 if I roll a 2, 15 if I roll a 3, -25 if I roll a 4, 5 if I roll a 5, and 0 if I roll a 6. So what do? Maybe I roll this die, let's say 12 times, and after I roll this die 12 times, I add up all of the numbers that I get. So if I roll a 2, I add up -5. If I roll a 5, I add up 5. If I roll a 6, I add 0. And I add up all those numbers, and at the end, there will be a value, and that's how many bonus points I get you. Now what's nice about this is maybe I roll a bunch of 3s. Say I roll 5 3s. Well, you get 75 bonus points on your exam. You could practically not take your exam and still get at least a C on the exam. But on the other hand, maybe I roll a couple 4s. So if I roll 2 4s, you've already got -50. And -50 bonus points means I take 50 points off your exam grade. Now, I should probably put a note here. No grades will be harmed from this particular experiment. Or maybe they will. I don't know. Let's see. I put the note there, though, so it's probably obvious that I won't hurt the grades. But maybe we'll do it. So let's take a look and see what happens. So let's try this out. So I'm going to roll a die. And remember that if I roll a 1, it's 10 points, 2 is -5 points, 3 is 15 points, 4 is -25 points, 5 is 5 points, and 6 is 0 points. I'm going to roll it, let's say 12 times, and we'll see what happens, how many potential bonus points you can get on your exam. So I got a 4, Oh, negative 25 points. So that was a 2, so negative 5 points. There's a 1, so that would be 10 points. A 2, so negative 5 points. A 4, so negative 25 points. A 1, so 10 points. A 1, so 10 points. A 3, so you get 15 points. A 3, so 15 points. A 3, so 15 points. Let's see here, you got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have 2 more rolls. So let's hope that we can get some more points going here. A 3, so 15 points. And a 4, so minus 25 points. So let's see how many bonus points you would get on the exam. So we got negative 25, negative 30, negative 20, negative 15, negative 40, negative 30, negative 20, negative 5, 10, 25, now we're up to 40, and then 15. So this is equal to 15 points. That's crazy. I mean, we rolled it 12 times. You could have gotten 15 points every single time, but you didn't. We rolled it, you could have gotten negative 25 points every time, but 15 bonus points. Okay, now I'm not actually going to give you 15 bonus points, but one of the things I want to show you is that the 15 doesn't seem like all that much. How come we didn't hit a bunch of 15s or 10s? I mean, if I would have rolled a 10 all 12 times, then you would have gotten 120 points. It doesn't seem that far off. Or I could have rolled 10s and 5s and 15s and 0s, and you just would have gotten positives, but we kept on rolling that negative 25. So what I want to talk about is what's called the expected value. So I'm not going to give you 15 points on your exam, but let me show you why it didn't get even higher than that to make it even more exciting. And that's for the expected value. The expected value is what the average amount of points you should expect to get each time you roll the die. So, or each time you run the probability experiment. So the idea is that 1/6 of the time we should have expected to get 10 points. And 1/6 of the time we should have expected to get 5 points. And 1/6 of the time we should have expected to get 15 points. And 1/6 of the time we should have expected to get negative 5 points. And 1/6 of the time we should have expected to get 25 points, negative 25 points. And 1/6 of the time we should have expected to get 0 points. So what the expected value does is it multiplies the probability that you get that value times the value that you get. And then you add it up for all the probabilities. So the idea is that in the 12 times that I rolled the die, I would have expected to get 2 10s, 2 5s, 2 15s, 2 negative 5s, 2 negative 25s, and 2 0s. That's 1/6 of the time for each of the rolls, each of the values. So if I take 1/6 times 10, I get 10 out of 6. 1/6 times 5, I get 5 out of 6. 1/6 times 15, I get 15 out of 6. 1/6 times negative 5, I get negative 5 out of 6. 1/6 times negative 25, I get negative 25 out of 6. And 1/6 times 0, I get 0 out of 6. Add this all up. 10 plus 5 is 15, plus 15 is 30, minus 5 is 25, minus 25 is 0, so I get 0 out of 6, which gives me 0. The expected value is 0. What that means is, on average, if I keep on rolling the die, on average, over a long period of time, I would expect that I would get 0 points each time. And had I kept on rolling the die for our experiment on the previous slide, I would have noticed that I would have kept on bouncing up and down, but I would have been sticking around 0. Sometimes it would be positive, sometimes it would be negative, but overall, on average, I'd be getting closer and closer and closer to 0 as the average number of points that I got per turn. In fact, if you look at it, we got 15 points out of 12 turns. It's a little bit above 1. It's not a very large number we were getting on average when we rolled it. And had I rolled it again, I might have gotten a negative 25, and that would put us to negative 10. Right? And I would have gotten something that was actually negative. So the expected value is your expected value, your average value, each time you run the trial. And so this is how you calculate it. You multiply the probability of that event, multiply by the event, its numerical value, and you add it up for all of the outcomes. That's it.